Okay, so just one more thing. We talked about surfaces which the equation which describes them has degree 2, right? And we call them quadric surfaces. They had degree 2. And sphere, ellipsoid, hyperboloid, elliptic cone, saddle, there were different examples of that. But what if we have an equation for a surface which degree is 3? For example, what if our surface is described by an equation like this, say x cubed minus y cubed equals z, something like that, or x cubed plus y squared z equals, say, y. So the degree means the highest degree in one equation. So for example, here the degree is 3, here the degree is 3, here the degree is 1. Or here the degree is 3, degree of this term is also 3 because it's y squared, and then for z it's 1, the total degree is 3, and here's 1. So when I say degree of an equation, I mean the highest degree which appears in an equation, okay? These equations called cubic, and they look different. They don't look like the surfaces we saw earlier. They kind of look different. They are not similar to the surfaces we saw before. So how do they look like? If we see them, can we kind of understand the difference? Do they look similar? Well, I can show you one example here on Wikipedia. Let's look at one example just to see how they look like. Okay, this is an example of a cubic surface. As you can see, this is not similar to the surfaces we saw before. It's not similar to ellipsoid or hyperbola or paraboloid or anything of that kind. Actually, it's a cubic surface, and this is another example of a cubic surface, as you can see. As you can see, they kind of look like each other. They have their own form. These are examples of some surfaces of degree 3. What about degree 4? Well, degree 4, the equations of degree 4, they are different. They don't look similar. So here we have, so we might have surface which the equation which describes the surface is degree 1. If the degree is 1, we would have just a plane, simply a plane. We might have a surface which the equation which describes it has degree 2. These are all the surfaces we saw: sphere, ellipsoid, hyperboloid, etc. Some surfaces, and these are called linear, these are called quadric. Some surfaces have degree 3. They are called cubic. The example we just saw was one of these surfaces. They're harder to sketch. It's hard for me to sketch them too, but they kind of look like this. They're kind of more complicated kind of surface. Now we have surfaces of degree 4. And actually these surfaces are important. They're important in math. They're very important in physics. They're very important in string theory. There is a very important example of these surfaces known as K3 surface. So the surfaces of degree 4, the name for them, what do we call them, is quartic surface or quartic equation. And let me show you. Well, it's hard to get a grasp, get a feeling of them, but let me just show you one photo of a surface of degree 4. This is a picture of a surface of degree 4. As you can see, again, it doesn't look like the things we've seen before. So we have these surfaces of higher degrees, and they get more and more kind of, well, I mean, I can't say they get more and more complicated, but they're more complicated than quadric surfaces. Okay, the goal was just showing them to you. Nothing important here. Okay, so let's start with partial derivative. Well, before going that, the last picture I showed you was a picture of a surface of degree 4. It's called K3. This surface is very important surface because it actually comes from a very important 4-dimensional space, which of course we can't talk about, but it's related to a very important 4-dimensional space. Why do they call it K3? Because it's kind of this 4-dimensional space, the understanding of this 4-dimensional space is based on a work of 3 mathematicians. In the honor of those people, it's called K3. Their names are Kummer, Kähler, and Kodaira. And because of these 3 mathematicians, this surface is named K3 surface. Anyway, let's continue with our partial derivatives. So when we have a function which is not single valued, we have a new concept called partial derivative. What does it mean? So let's go back. What does derivative itself mean when we have a function, say f, from R to R? What does derivative of this function really mean? Derivative is actually a kind of rate of change, right? It shows how function changes when you change x. So derivative, which we showed with usually f prime of x, or partial y, partial x, means it's kind of the rate of change of the function f with respect to x, okay? So it means if I change x a little bit, how y is going to change. So if you remember the accurate definition, the definition of derivative at the point x is equal to the limit of f of x plus, say, epsilon minus f of x over epsilon when epsilon goes to 0. That's derivative of a function. That's the way to compute or to define derivative of a function. But let me just write down 1 or 2 simple examples for the people who have forgotten that. So if f of x is, say, x squared, if I ask what is derivative of f, it would be, what is the derivative of f? So what is f prime of x? It would be just limit of f of x plus epsilon. Here it would be x plus epsilon squared minus f of x, which is x squared, over epsilon, where epsilon goes to 0. Well, we can expand x plus epsilon squared. It's x squared plus epsilon squared plus 2x epsilon minus x squared over epsilon. Now x squared cancels with minus x squared. We would get the limit of epsilon going to 0 of epsilon squared plus 2x epsilon over epsilon, which is equal to, well, I can cancel one factor of epsilon in numerator with denominator. I can write the numerator as epsilon times epsilon plus 2x over epsilon. And I can cancel this epsilon here with this epsilon here. I would get the limit, epsilon goes to 0, of epsilon plus 2x. Well, epsilon is going to 0, this goes to 0. We would get 0 plus 2x, which is just 2x. So the derivative of x squared is 2x. So as you can see, this definition, limit of f of x plus epsilon minus f of x over epsilon, can be understood as the instant change of f with respect to x. What do I mean by that? I can rewrite it as f of x plus epsilon minus f of x over x plus epsilon minus x. Okay, where epsilon is going to 0. So in our domain, we have x, and then in our range, we would get f of x. In our domain, we have x plus epsilon, then we would get f of x plus epsilon. So here in numerator, we have changes in value of y. So here we have x, here we have y. Here we have changes in the value of y. Here we have the changes in the value of x. And this is the ratio of change of the value of y over the x. So this shows the rate of change of y with respect to x. That's what the derivative really means, independent of how we can compute that. Okay, there is one comment. Someone wants to look at this slide again. Well, here we have just the definition of derivative, and using that definition, we computed the derivative of x squared. Okay, if there is no question, we can continue. Okay, so when we have a function of two variables, say f of x and y equals z, we can again ask what is the rate of change of z. But then I would ask, with respect to which variable are you interested in? What is the rate of change of z with respect to x, or you are interested in the rate of change of z with respect to y? Which one? So they are different, and we use different notations. So the first one is called the derivative with respect to x. Second one is called derivative with respect to y. For the first one, we show this notation, derivative of f with respect to x. For the second one, we show this notation, derivative of f with respect to y. Another notation sometimes people might use, especially the book uses this notation, is derivative of f with respect to x. Usually the way it's written is by f sub x. It's noted by f sub x. And derivative of y, f with respect to y, f sub y. Just another notation. But the computation, it's usually called round. It's kind of like df dx, but we use df dx, so when we had just functions from fr to r, we used to show df dx. That was another notation for derivative of f with respect to x. When there is more than one variable, when there is both x and y, when we want to take derivative with respect to x, just to mention there is another variable, there is a convention. We use kind of, as you mentioned, curly d, or which is, we call it here partial f, partial x, or round f, round x, or also partial f partial x. Anyway, if we forget these concepts, the computation is pretty simple. So suppose I have a function of two variables. Suppose I have a function from R2 to R. Suppose this function f of x and y is x squared plus 3xy plus y cubed plus 3. Okay? And I want to compute derivative of f with respect to x, partial f, partial x. What it means is that I should assume, the only key point is that I should assume the other variable, here y, is constant. So I should assume the other variable, here y, is a constant, just like 2 and 3. What is derivative of a constant? It's 0, right? Okay. So we are taking derivative with respect to x. We should take derivative of the first term. Derivative of x squared is simply 2x plus. What is derivative of the second term with respect to x? It's 3xy. Well, when I have something times x, a number times x, like 4 times x, derivative of this thing with respect to x is just a constant number. I am multiplying x with that number. Here it's 3. But I'm assuming y is another constant number. I'm multiplying x with that. So that's also a constant number. It would be 3y. So the derivative of 3xy with respect to x is just a constant number. I'm multiplying x with that one. And that's 3y because I'm assuming y is also a constant number. What is derivative of y cubed? Well, I'm assuming y is constant. Derivative of constant numbers when they're alone is 0. What is derivative of 3? Well, 0. So partial f partial x is 2x plus 3y. Okay. What about derivative with respect to y? Let me write that down up here. We don't need to go to the next page. So what is derivative of f with respect to y? Now I should assume the other coordinate here, x. I should assume the other variable here, x, is a constant. Okay, derivative of x squared would be 0 because x is constant. What about 3xy? Okay, I'm taking derivative with respect to y. So for example, derivative of 4y, if I take derivative of that with respect to y, if I take derivative of this thing with respect to y, it would be the constant number I'm multiplying y with, right? Just 4. Now here, I'm taking derivative of 3xy with respect to y. It would be the constant number. I am multiplying y with that, which is 3x. X is also a constant number. I'm multiplying y by that number. What is derivative of y cubed with respect to y? It's 3y squared. What is derivative of 3? 0. So the derivative is 3x plus 3y squared. Partial f partial y is 3x plus 3y squared. That's how we compute the partial derivatives. Okay. Let's do one more example. Say I have f, x, y, and z. Suppose I have, let's call that w. Suppose I have a function defined on the 3-dimensional space to R. Let's say the function is equal to x e to the x squared y z plus y z. Okay. We start with partial f, partial x. I should start with this term. this term itself is multiplication of two functions. It's multiplication of x, that's one function, with the other function, e to the x squared yz. I'm multiplying two functions. Now, when I want to take derivative with respect to x of a multiplication of two functions, I should use the product rule. What does the product rule say? It says derivative of f with respect to x would be the derivative of the first function. Here, derivative of x is 1 times the second function plus derivative of the second function times the first function. So plus x times derivative of the second function. Now, what is derivative of e to the x squared yz? Well, both y and z are constants now. So because I'm taking derivative with respect to x, I am assuming the other variables, here y and z, are just constant numbers. Okay, what is derivative of this thing with respect to x? Well, when I have e to some power, the derivative would be first derivative of what I have in the exponents. Derivative of x squared is 2x. And then there are these constant numbers. I'm multiplying x squared with them. So I should just write down those numbers. Derivative of the exponential map, e to something, is itself, is e to whatever it is, multiplied by the derivative of the exponent. So that would be 2xyz, e to the x squared yz would be the derivative of e to the x squared yz. And then derivative of yz with respect to x is 0. So that's the partial derivative with respect to x. What is the partial derivative with respect to y? What's the partial derivative with respect to y? Well, here I should assume x, y, and z. I should assume only y is a variable. X and z are constant numbers. So here there is no need to use product rule anymore. Well, in some sense, because x is a constant there, I don't have anything to do with that. I should just take derivative of this function. In some sense, this is product rule, but it's a trivial product rule. I should take the derivative of this function with respect to y. Well, when I want to take derivative of e to the x squared yz with respect to y, first, I should take derivative of this part with respect to y. But y, I've multiplied y by x squared z. But if x and z are constants, x squared z is also a constant. So here I have y multiplied by a constant, x squared z. X squared z is just like 2, for example. So derivative of x squared yz with respect to y is just the constant. I'm multiplying y with that, which is x squared z times e to the x squared yz. And derivative of yz with respect to y, well, z here is just like a constant. If I take derivative of yz with respect to y, it would be the constant I'm multiplying y with. So it would be just z. Okay. What is partial derivative with respect to z? Well, again, I should take derivative of the first term. X here is constant, a coefficient. I should take derivative of the exponential map, e to the x squared yz. So I should first take derivative of x squared yz with respect to z. Now this time, x squared y is constant. We're multiplying z by that constant. So derivative of x squared yz with respect to z is the constant. I'm multiplying z with that. So it would be x squared y, then ex squared yz. Plus then derivative of the second term with respect to z, which would be the constant. I'm multiplying z with that. So that would be y. So I would get the 3 derivatives: derivative with respect to x, derivative with respect to y, and derivative with respect to z. And these are the three things we have. Okay. Okay, there is, we can use this to compute, well, maybe I should go one step back. When we had functions from R to R, something like this, single valued functions. Derivative of f with respect to x, which is f prime of x, we can compute that, but it also has a geometric meaning. So for example, if this is some point x, the geometric meaning of f prime of x is the slope of the tangent line at x, of the tangent line to the graph of the function at that point x and y. Okay, this is here f of x. That would be the slope of this thing. Now, the same thing holds in higher dimensional case, but it is slightly more complicated. So for example, suppose I have a function f from R2 to R, where f of x and y is x squared plus y squared. If we look at the graph of the function, it looks like this. It's a paraboloid. It's the graph of the function, right? At each point on the graph of the function, so suppose x, y, z is a point on this surface. One person might ask, what does the derivative mean? What is the geometric meaning of the derivative? In the previous case, we said that the geometric meaning of derivative is the slope of the tangent line. But here you can say which tangent line? Well, if x is a point, say here, xy is a point here, there are two interesting tangent lines. One of them is I can walk in x direction. You see, y is not changing if I walk in the direction of the red arrow, right? I'm walking in the x direction. There is another direction, walking in parallel to y. I can walk in the y direction, right? Parallel to y axis. Or I can walk parallel to the x axis. Now, if I walk parallel to x axis, I can see what would be the tangent line on the graph of the function if I walk in the x axis. So if I walk at this axis, different points would have different values on this thing. And then I can look at the tangent line on this surface in the x direction. I can look at the tangent line on this surface at the y direction too. It might be like this. If I look at the tangent line in the y direction, you can do that. If you have a bowl or something which looks like a kind of paraboloid at your home, at each point you can look at the tangent to that thing in direction of x, and you can look at the tangent in direction of y. The slope of this tangent line in direction of x is partial f partial x, and the slope of this tangent line in direction of y is partial f partial y. So for example, if we have a question like this, if we have a function f of x and y, which is equal to, say, minus x squared over 2 minus y squared. You have this function. F is a map from R2 to R. It's a function or map from R2 to R. One might ask us, for example, at some point, say 1 and 1, at the point xy equals 1 and 1, find the slopes of the lines tangents to the graph of the function in the x direction and in the y direction. That's the question. Okay, so I can sketch the graph of this function. The graph of this function would be, it's kind of like x squared plus y squared, but it has negative, right? It's minus x squared over 2 plus y squared. So it's a paraboloid, but it's minus that. Just like y equals x squared looks like this, and y equals minus x squared looks like this. The minus the paraboloid, the familiar paraboloid, we know looks like this thing. Point 1 and 1 is here, and f of 1 and 1 is minus 1 over 2 plus 1, which is minus 3 over 2. So this point on the surface of this function is 1, 1 minus 3 over 2. Now I can start to walk on the x direction, but I suppose this is a mountain. Again, this analogy of mountain is what I'm using a lot actually. So suppose you are climbing this mountain, actually you're going down now. Suppose you want to walk in the direction of x, but you are in the mountain. So if you want to walk in direction of x, but you're on the mountain, you would start to come down, right? If you try to go parallel to x-axis, but if you are on the mountain, you would go down like that. The tangent line to your trajectory would be like this. If you want to walk in the parallel to y direction like that, you would go down like this. The tangent line would be partial derivative, partial f, partial y. So the slope in the x direction would be partial f, partial x, which means I should take derivative of this function with respect to x, minus x is the partial derivative of the first thing, partial derivative of the second thing is 0 because you're taking derivative with respect to x. And the point is x and y equal 1 and 1. So x is 1 and y is 1. So if x is 1, the slope would be minus 1. Now, what is the slope in y direction? If you are really climbing that mountain, if you walk in the x direction, the slope you would feel is minus 1. If you walk in the y direction, the slope you would feel as a person who is climbing that mountain would be derivative with respect to y, which is minus, well, derivative of the first term is 0 when we are taking derivative with respect to y, and the second term derivative is 2y, so it would be minus 2y. And at that point, 1, 1, y is 1, derivative would be minus 2. So if you walk in y direction, derivative you would feel would be minus 2, which is different. If you walk in x direction, derivative is minus 1. The minus sign here means you are going down. So if the derivative, if the slope is positive, it means if the slope is, remember, if it's positive, it means you're going up. If the slope is negative, it means you're going down. If the slope is 0, it means you're horizontal. If the slope is infinity, it means it's vertical. Okay. That goes for that. Now, we can use, there are other, well, ways we can use partial derivative. Is there any question up to this point? Is everything going smoothly? Or is there any source of confusion? There is no derivative. No, well, z is like the not in the domain. We take derivative with respect to things in the domain. So the answer is no. Okay. Okay, now we can use this idea a little more. As I said, derivative, what it means in application is rates of change. Partial derivatives, which is we have now, means, well, rates of change in different directions. Well, we can see that in few examples. So remember, well, I think we had that in the exam too. If you have a parallelogram, something like this, with sides A and B, we can compute its area, okay? The area was equal to, does anyone know what is the area here? If the length of one side is A and the length of the other side is B. That is correct, but because here we are in two-dimensional case, we can kind of, it's length of the inner product, that is correct. Does anyone remember what is the length of the inner product? So it's the length of cross product, I'm sorry. It's the length of the cross product. Does anyone remember what is the length of the cross product? Yeah, that's, there was another way. If you remember, there was another formula. The length of the cross product is the length of A, the length of B, sine of the angle between them. Say here it's theta. That is true. Now we can see that directly. Actually, if you know a little Euclidean geometry, you really don't need the cross product. Why is that? Let me try to sketch a. We can actually prove this very simply. So one side is B. The other side is A, right? And so it looks like this, correct? And I want to compute the area of this thing. One thing to note is that if I look at the orthogonal line here and the orthogonal line here, and if I connect these two, I would get two triangles. This green triangle and this blue triangle. Actually, these two triangles are equivalent, right? Is it clear? They have the same area because, well, these two sides are the same, these two sides are the same, and these right angles are the same. Also, this angle is equal to this angle, and this angle is equal to this angle. So they have the green triangle and the blue triangle, they're equivalent, and they have the same area. What does that tell you? It tells you, rather than computing the area of this thing, I can remove this one, bring it here. What would I get if I bring this triangle and put it here? What I'm going to get is a rectangle. I would end up with a rectangle. And I know how to compute. So the area of this thing, the area, I would erase this one. The area of this thing is equal to the area of the rectangle, which is formed by moving this green triangle here. Okay? Does that make sense? Now, what are the sides of this rectangle? Well, this side is still B, right? This part plus this part is B. I have this part and I brought this green part here. Well, the sum is still B, correct? What is the other side of this rectangle? What I know is that this length is A and this angle is theta. What is the other side of this rectangle? Does anyone know? Yes, it's A sine of theta. So I have a rectangle. One side is B, the other side is A sine of theta. Well, assuming A and B are positive numbers, it's the area of this rectangle, but it should be equal to the area of parallelogram. So that would be the area. So we can't do it without linear algebra. We can do it just using simple Euclidean geometry. But now that's not the question. Now the question we have here is that here we have B, here we have A, here we have theta. We get something like this. And we have area. Area is equal to AB sine of theta. I can think about area as a function defined on R3 to R. It's a function which takes 3 variables. What are those 3 variables? One of them is A, one of them is B, one of them is theta. Area depends on these 3 numbers, right? You should have these 3 numbers to know what is the area. So it takes 3 values and then give you 1 value back, okay? Now, one person might start to change A a little bit. Okay, if you change A a little bit, for example, if you increase A very little, the area of this thing will change. How much does F depend on A? What is the rate of change based on A? So what is the rate of change of area with respect to A? For example, when A is, say, 10 and B is 20. When they ask us a question like this, it means we should take derivative of this function with respect to A. Actually, for people who are interested in economics, this is the base of the application to economics. Not for area, for other functions, I would mention how it's related to maximizing or minimizing a function. Okay, I should take derivative of F with respect to A. Well, here I'm multiplying A by B sine of theta. Because I'm taking derivative with respect to A, I'm assuming B and theta are constants. If B and theta are constant, B and sine of theta are constant. I'm multiplying A by this constant, so derivative with respect to A would be that constant. Oh, I should also fix theta. Say theta is pi over 6. So here it would be B, which is 20 times sine of pi over 6, which is 1 over 2. The result of multiplication would be 10. That would be the rate of change of F with respect to A. So one person might ask, what is the rate of change of F with respect to theta? What does that mean? It means if I change theta a little bit, if I increase or decrease theta a little bit. How the area is going to change. In order to understand that, we should take derivative with respect to theta. Well, if our variable now is theta, then A and B will be constant. So we have just AB there. And we should take derivative with respect to theta. What is derivative of sine with respect to theta? It's simply cosine. So here A is 10, B is 20 times sine of pi over 6, which is, oh, sorry, cosine of pi over 6, which is the square root of 3 over 2, would be 100 radical 3. That would be the rate of change with respect to theta. Now, why this thing is important? Why did I say this is important for economics? Well, when you have a function f of x and y, or even more variables, you can have as many variables you want. I would write it for 2, but there is no limits. You have 2 variables here, x and y. They can be anything. Suppose f is a function which you want to maximize. Okay? So if you look at the graph of the function, if you maximize like this, what you can see is that the tangent lines would be horizontal. So if you maximize, or if you want to minimize, the important point is that tangent lines at those points are horizontal. What is the slope of horizontal lines? The slope, yes, is 0. Therefore, all the partial derivatives should be 0. So if you have a function f and you want to see if a point is really a max or mean or not, you should only see if the partial derivatives are 0 or not. That's the question you should ask yourself. So for example, if your function f of x and y is, say, x squared plus y squared, what about sign change? What do you mean? Do you mean about how you would understand if the, oh, you mean how do you know if it's max or mean or its saddle point? Is that your question? Would you elaborate? Are your question identifying between max or mean and the saddle? Okay, max or mean. I would explain that, yeah. So suppose you have a function like this, 2x. Yeah, you should look at the second derivative. Plus 2y, say plus 10, okay? And you want to see where is the max. I would claim the max happens at the point x and y equals -2, -2, right? That's my claim. Max happens at the point -2, -2. Well, sorry, it's not max. This is, my claim is wrong. Actually, you would minimize f at that point, at -2, -2. So I claim the minimum of f happens at -2. So if this is the amount of, so say, money you should spend in order to do something, you want to find the minimum value, right? So I'm saying that point, the point which gives you the minimum is -2, -2. In order to check that, we should take derivative. Derivative with respect to x is 2x plus 2. Derivative of f with respect to y is 2y plus 2. At x equals to minus, oh, it's -1, -1. Another silly mistake, sorry. -1, -1. When x is -1, we get -2 plus 2, which is 0. Here we get -2 plus 2, which is. But is derivative being 0 enough to decide if it's max or mean? No, not necessarily. First of all, we should understand if it's max or mean, and then we should understand, I mean, it's not necessarily max or mean. So for example, consider this one. You might have something, a function which it's going to increase. For a second, its derivative becomes 0, and then it increases again. So here, if you look at the tangent line here, you can see the tangent line is horizontal. Therefore, the slope is 0. But the derivative, which is 0 here, being 0 does not imply you have max or mean. So if you have max or mean, That would imply derivative is 0, but not the other way. So here we have an example of something which the derivative is 0, but not, it's not max or min. How do we understand, when do we understand if it's max or min? So there, if the answer is by looking at the second derivative, but second derivative in higher dimensions is not very trivial. There is no well-defined second derivative in the sense we knew in the first derivative things. So for example, in one-dimensional case, you look at x squared, for example. The first derivative is 2x, the second derivative is 2. In Calc 2, probably, I guess, whenever the second derivative is positive, we would say it's mean. So if the derivative is 0, so if derivative is 0, and if the second derivative is positive, we would see a mean. That's what we had in for single valued functions. If derivative is 0, and the second derivative is negative, we would have max, like y equals minus x squared. Well, what is derivative here? Derivative is minus 2x. At x equal to 0, minus 2x is 0. Minus x squared looks like this. This is minus x squared. At derivative is minus 2x. When x is 0 here, derivative would be 0, as you can see. The second derivative, it means if we take derivative one more time, would be minus 2. It's negative. That would tell us we would have max. Now, the question is that, do we have something similar in higher dimensions? The answer is yes, but it's slightly more complicated. We would get to that. We would come back to this, not now, but we will come back to this notion of second derivative in higher dimensions. Okay. Okay, so let's look at a few more examples. I want you to solve some examples. So maybe just I would give you a few questions to think about them a little more to make sure we learned everything we talked about. So first of all, find the limits. First of all, show if the limit exists or not, and find the limits. Here, note that because here we have radical x and y, I'm assuming both x and y are positive. So their sum would also be positive. That's what I mean by these small positive signs above 0 here. I'm not assuming x and y are negative. I'm taking limit, but I'm assuming both x and y are positive. Okay, think about these two questions for a few minutes, and then I would solve this, and I would give you 2 more questions about derivative. Okay, we have one answer. Does not exist and 1. Okay, we would try that to see if that's really correct. Okay, So let's look at the first one. So xy over x squared plus y squared. Actually, I also think this doesn't have a limit. So I try to show this one does not have a limit. So let me tell you a trick. Here, the degree of numerator is 2. It's 1 and for x, 1 for y. The degree of the numerator is also 2. Here we have second degree, here we have second degree. We are adding them, not multiplying, so the degree is still 2. Let's see what would happen in this case. So I can go towards the center, the origin, which I'm computing the limit on x equals y direction. If x is equal to y, xy would be x times x. And on the numerator, I would have x squared plus x squared. It would be x squared over 2x squared. It's 1 over 2. So along this line, all the values are 1 over 2. So we have 1 over 2. Doesn't matter how close to the origin we are. Along this line, the value is 1 over 2. Let's take another direction. Y equals minus x. What would happen along this line? Well, x times y, but y is minus x over x squared plus y squared, which is minus x squared. We have minus x squared in the numerator, 2x squared in denominator. If I cancel them, I would get minus 1 over 2. So along this line, I have minus 1 over 2. So if I look at a very small region around 0, the points which are red, they have the value 1 over 2. The points which are blue, they have value minus 1 over 2. So there is no way, unique way, there is no way to extend the function continuously to the origin. So no limits. And it's non-removable singularity. Actually, the trick is usually, not always, that's not an answer, that's just a way of guessing. Usually, when the degree in numerator is greater than the degree in denominator, we have limits. So for example, if here we had x squared, y squared, the degree here would have been 4, then I would have guessed this function has limits, but at 0 and 0. But when the degree is in the numerator is not larger than denominator, usually I wouldn't guess that we have a limit. Okay. Anyway, so no limit. What is the second thing? It's x over square root of x plus y. So what is the degree in numerator? It's 1. What is the degree in denominator? Well, degree of each of them is 1. We are adding them, not multiplying. So the degree of addition is still equal to 1. Then we take square root. Well, then it should be something like 1 over 2, the degree. So the degree of numerator is larger than the degree of denominator. So we might guess that this one has limits. So because 1 is greater than 2, my guess, it might not always be correct, but my first guess would be we have limits. Now, I guess, well, my guess is we have limit, but what is the limit? So I should first guess what is the limit of this function when x and y go to 0. Well, if you want to guess, again, look at this thing. Look at the domain. You know, there are different ways to go to 0, right? One interesting way to go to 0 is along this red arrow. What are the points on this arrow? The points are of the form x and y, where x is 0, right? on this arrow, every point, the first coordinate is 0. So for these points, f of x and y, which is f of 0 and y, is equal to 0 over square root of 0 plus y, which is 0 over square root of y, which is 0. So in this specific direction, if I go to the origin, the value I would get is 0. So if I want to guess there is a limit, it makes sense to guess the limit should be 0 because in one direction it is 0. Now I need to prove that. We go back to the concept of proof of the limit, that the limit exists and it's equal to certain value. So I want to prove limits of this function x over square root of x plus y when x and y goes to 0 and 0 is 0. What does it mean to prove? It means for every positive epsilon, there exists a positive delta such that if I take any point, x and y, which its distance from 0 and 0 is less than delta, then the value of the function at x and y, which is x over square root of x plus y, minus L, here the limit, which is 0, is less than epsilon. So the key is to finding this positive delta, this number delta, okay? So the condition I have here is x over square root of x plus y minus 0, its square root should be less than epsilon. Therefore, square root of x over square root of absolute value of x over square root of x plus y should be less than epsilon. Okay, what can I do? I want to show this thing is doable. I can do this. Well, that's what I want to say. And from this, I want to find this delta. What is delta? What is a good value for delta? What is the good choice of delta? Maybe that's better. That's the question. Okay, think about this. If you didn't get to this one, think about this for a few seconds to see what can you choose for delta. So we would have this thing. We want to have this. We want the function to satisfy this inequality. What should be the value? What should we choose delta to be? So the function would satisfy this inequality. Think for a few seconds. So let me explain if you don't have any idea. So look at this function, absolute value of x divided by square root of x plus y. Compare it to this new function, which I replace y with 0. Okay? Suppose, as I mentioned, suppose x and y are positive. That was part of the assumption. This function, does it get larger or smaller? Are we going to get bigger function, a larger function, or smaller? Which one is it greater or equal or less than equal? Yeah. So here, y is something positive, right? So denominator here is larger than the denominator here. But when you have a larger denominator, the whole fraction would be smaller. Okay? So it would be, say, less or equal than this thing. Now, if I want this function to be less than epsilon, it's enough to make sure this one is less than epsilon. If this one is less than epsilon, because the original function is less or equal than absolute value of x over radical x, then it's good, we're done. But on the other hand, we know absolute value of x over radical x is actually equal to radical x. It's square root of x. Why? Because absolute value of x is equal to radical x squared. So it's radical x times radical x. We can cancel one of them with the square root of x, which means x should be less than epsilon squared. Or maybe I just keep it as that. Radical x can be less than epsilon. That's what I want. Okay? But can we take delta to be the same as epsilon? I mean, what is the distance of x and y from 0 and 0? It's x squared plus y squared, square root of that, right? That's the distance of a point x and y from the origin. If I take delta to be equal to epsilon, if I take it to be that, it means this guy is less than delta, which is equal to epsilon. So I would know square root of x squared plus y squared is less than epsilon. Okay? Oh, let me think for a second. Okay, so actually not that. So if I take delta to be, I'm sorry, if I take delta to be epsilon squared, that would be helpful. Let me tell you why. So if I take delta to be epsilon squared, okay, I guess I'm making a small mistake here. Yeah, I think epsilon squared is good. So let me go to the next page, which we have enough space. So if I assume x squared plus y squared, its square root is less than epsilon squared, it means x squared plus y squared is less than epsilon to the 4. On the other hand, x squared is less than x squared plus y squared because y squared is a positive number. So x squared is less than epsilon to the 4. Therefore, x squared is less than epsilon to the 4, which means x is less than epsilon squared, which means absolute value of x is less than epsilon. Well, that's exactly what we want. Why? Let's go back. This is what we like to have. Square root of x less than epsilon. And the choice of delta equals to epsilon squared gave us that thing. So it's a pretty straightforward inequality. And that means the limit is 0. So I guess you should do a lot more examples in this about this specific thing if you are not really used to that. Some examples might be quite hard and complicated, but I'm sure after a while you would get a hold of it. You would learn how to manage this thing. Okay. So what time is it? Okay, maybe just do one more example. Okay, as you can see, derivative is easier than limits in some sense. Well, so suppose we have a function fxy equals to, say, y e to the y over x. What is partial f partial x and what is partial f partial y? Think about this one for 2 minutes. Compute these two partial derivatives. Okay, let me solve these two. So partial f partial x, it means we should suppose y is constant. So we have just y here, just like a constant number. And then we should take derivative of y over x. Again, y is constant there because, well, y over x is y times 1 over x. Y is just a constant there. I should take derivative of 1 over x, which is minus 1 over x squared. And then times e to the y over x, which is y squared over minus x squared e to the y over x. What is derivative with respect to y? Now we can use the product rule. Derivative of y with respect to y is 1. Therefore, 1 times y over x plus y times derivative of e to the y over x with respect to y. So again, I should first take derivative of y over x. But now with respect to y, so here y over x is y times 1 minus x. If x is constant, the whole 1 over x is also constant. So it comes out like a constant times e to the y over x. So we have e to the y over x plus y over x e to the y over x. Okay, and that's for today, but we have just a few minutes. So I would finish the class now. So goodbye the people who watch the class on the YouTube.